Okay, so today we are looking at endogeneity as another robustness test that we can consider whilst we are working on our PLS-SEM analysis. And we are going to use what we call Gaussian Copula approach in PLS-SEM. But first of all, what is endogeneity? Endogeneity occurs when an independent predictor, the independent variable or the predictor variable in the structural model is correlated with the error term of the dependent variable. So what we mean is that your variable x is supposed to explain only the dependent variable y. But in the case where x also has it is also associated with the unexplained path or the error term of y, then it means that we are going to have some consequences on the path coefficient or the beta estimate. And it can lead to bias or inconsistent beta value. All right, so that is the basic understanding of endogeneity. And this is a very serious problem in research, which I'm sure there are still debate on that now. For that matter, there are a lot of studies. For example, most of the top journals, if you want to really, publish in top journals, they're supposed to address endogeneity issues, both theoretically and then statistically, right? And endogeneity, most of the papers I've seen in SEM, they don't really talk about that. But if you really want to publish in top high quality journals, some of the reviewers might ask you how were you able to address endogeneity. So it is best that we learn that as well so that we can incorporate that in our research. So the standard assumption of PLS-SEM is that the exogenous variable or the dependent variable are uncorrelated with the error term of the endogenous or the independent. The exogenous variable, which is the independent variable, are uncorrelated with the error term of the dependent variable or the endogenous variable. So if this assumption is violated, that is where the endogeneity problem comes in. All right. So now, why is this a concern? Why does it matter? So if we don't consider this, it means that the coefficient that we have estimated can be biased. It can be over or underestimated. All right. The same way, once that is affected, our p-value and then the t-value can also become overestimated or underestimated. And for that matter, it becomes unreliable. Okay. And then our conclusions about our hypothesis may be wrong. So if you get p-value to be statistically significant, it means that your hypothesis, if it is now a hypothesis that you have stated, it means that it holds as you have stated it, right? So, or you reject your null hypothesis as you have stated it, and then you go for the alternate hypothesis. So the p-value, if it is 0.00 and there is an issue with linearity, if you address this issue, or if you consider addressing this issue, it can turn out to be insignificant. For that matter, that is where the conclusions you make on your hypothesis becomes correct or accurate. And then reviewers also increasingly expect individuality checks, especially in the economics field. There are so many, anytime you do any research in econometrics and you don't address this issue, the reviewers might ask you to address that. And in social sciences, it is becoming more common that they will ask you to address these issues. So let's look at the sources of individuality in PLS-SEM. One of the most common source is omitted variable. So a variable that affects X, that is our independent variable, and then y, our dependent variable, is left out of the model. So there, it can be that there are some variables that are omitted. In that case, we call it omitted variable. So this creates a hidden correlation between x and the error term. So, for example, ability is omitted from a model where education and income. Okay, so since ability affect both education and income, the education effect is biased. So sometimes when you are considering a model, there might be some hidden variables that need to be considered. Because anytime you construct a model, we have the part that is being explained. That is where we have the R square. So the part that is not explained by the independent variable, it means that when we reconsider adding other variables, the R square will improve. So once we have about maybe 0.3, it means that about 0.7 of our dependent variable is not explained by the independent variable. Okay, so that's 70% left, or 0.7 that is left are all possible omitted variables, which when we consider will improve our R square value. Okay, so omitted variables are most common source of endogeneity. Okay, and that common source of endogeneity is measurement error. So when constructs are poorly measured, in that case, you might have low reliability. And then the measurement error becomes part of the structural error, inducing correlation with what? The predictor. So it can happen that if you don't really go through the right processes, setting up right questions for your respondent, in that case, there can be measurement error, and which can lead to low reliability and can also affect your validity as well. So in that case, it can have effects. It can induce correlation with what the predictors. And then we also have simultaneous causality, or what we call reverse causality. So it could be that X can affect Y, and at the same time, Y can also affect X. So, for example, advertisement can affect sales. In the same way, if you have high sales, it can also influence you to have more advertisement as well. Yeah, so that is another cause of endogeneity. So if there is reverse causality, if X can affect Y, and then Y can also affect X. And then the last one is common method variance, which is CMV. So when both X and Y are measured using the same method. So this is very common in survey. So, and then it also normally happens when the respondents are the same. So mostly with primary data, the reviewers will ask you, if you don't address common method bias, they can ask you to how were you able to overcome these issues. Okay, because it is very common in primary data. For example, if you have a very lengthy questionnaire, sometimes the respondents do not really pay attention to the statement within the questionnaire. So you realize that they will just be taking, and this can have issue with what they call common method variances. So it will lead to common method bias, right? So why should you and then I, as a researcher who want to use PLS-SEM, care about this? According to Holt et al., 2018, he says that PLS-SEM researchers have largely overlooked endogeneity. And this is very surprising because PLS-SEM is grounded in regression. So far as you're doing regression, endogeneity is something that has to not be overlooked. Okay, because endogeneity is a very common problem in regression analysis. And PLS-SEM is also a form of regression analysis, right? And then top journals now will require you to strongly address issues, how you're able to tackle endogeneity. And if you don't do that, it can lead to rejections. It can lead to misleading particular implications or maybe retracted conclusions. Okay, your conclusions might not be reliable. Now, the good news is that Smart PLS has an inbuilt tool, which we refer to as the Gaussian Copula approach. And this will help us to detect, and not only detect, it will help us also correct the endogeneity that has been identified in the study or in the data or model. And it is also an instrument-free approach. Okay, you don't need to find any external instrumental variable. So it happens that with other area or field like economics, there are so many ways to address endogeneity. And one way is what you call the instrumental variable. So you have to introduce what you call an instrumental variable that will affect that will not have any effect on the dependent variable, but will have effect on the independent variable. So that variable is what we term as instrumental variable. But with this Gaussian Copula approach, it is an instrument-free approach. So you don't need to go and look for an external variable that will be used for checking or addressing endogeneity. So let's look at some of the approaches to handle endogeneity. And one of the very common ways to address endogeneity in SEM is the introduction of control variable. Okay, so whenever we establish a model, we have to also consider adding some other factors constant. And in PLS, some of the common factors that we hold constant is the demographic variables, the genders, age, and the rest. Okay, but it is not normally common in some studies. Probably they have done that. If you do that, then the result is insignificant. It does not really affect the study. Okay, so it means that these demographic variables do not really affect the dependent variable. So that is how come most of the times you don't see control variables in SEM. But one way to address that is adding control variables. Okay, and the advantage is that it is very simple to implement. And then the disadvantage is that it may not fully solve the endogeneity problems. And then we also have the instrumental variable, as I rightly explained earlier. So here we use an external variable that is correlated with X, but not with the error term. And then the advantage is that strong correction if valid IV is found. If you're able to find a strong or valid instrumental variable that will correlate with the X, the independent variable, and not the error term, it means that it is a very strong way to address endogeneity. And the disadvantage is that it is not very simple to find a valid instrumental variable. And if you find an instrumental variable that is very weak, it can cause more endogeneity problems. So perhaps the Gaussian Copula approach is something that is very easier to go about, and it models the correlation between X and the error term directly using the Copula function. So all of these things are inbuilt within the PLS-SEM. And then the advantage is that there's no need for any external instrumental variable because it's already built into the software, the Smart PLS. All right. So it means that if you're using any other software, for example, with SEM, you can also use R to do that. We have packages in R that can also help us to construct PLS-SEM models. Even you can also have access to PLS-SEM with Stata. Okay. And then we also have another software called WAP PLS. And also, I think I've also heard of M+. It's also very common software that you can also use to do PLSM. But so far, I think that the simple approach or the simple software and easier, user-friendly and graphical friendly is the Smart PLS. Okay, so it also already has the inbuilt coupler function. So we don't need to introduce any new variable. And the disadvantage is that it requires non-normality of the predictor variables. And also it needs larger sample size. So it is recommended to always first include control variables and then apply the Gaussian Copula as a statistical tool or as a robustness check. So before I started, I mentioned that um, we can also use the Gaussian approach, the linearity, as a robustness check to validate our findings. So, and this is the second approach. Instead, we looked at the linearity approach, the non-linear reaching the quadratic effect function. So, what is the Gaussian Copula approach? What is the Gaussian Copula approach? The core idea is that if endogeneity exists, then there is a hidden correlation between the predictor and then the error term of X, of Y. So the Gaussian Copula approach directly models this correlation by adding an extra term, which is called the Copula term, the regression coefficient. So with the standard PLS that we know, our Y is equal to our beta coefficient and then the X or the predictor variable plus the error term. Now, once we factor the Gaussian approach, it introduces a new term, which is the BC, multiplied by the CX. So the coupler term, so here, plus the error term. So here, the CX, the new term that has been added, the CS is the coupler term, which is equal to the function we see over here. And then the BC is the coupler coefficient. That is the proportion to the correlation between X and the error term. And then the E is the error term. That is the corrected error term. So if you are to interpret that, if the coefficient, the coupler coefficient is significant, it means that endogeneity is present. And for that matter, the coupler corrects for it. So the software automatically also corrects the coefficient for us. And if our coefficient is not significant, it means that there is no endogeneity issue. So in that case, our already established model is significant. All right. Let's look at the key requirements and assumptions. So before we conduct this Gaussian Copula approach, it is always advisable to check that your predictor variable is non-normal. Okay, so the potential endogenous predictors must be non-normally distributed. And the reason is that if the predictor is perfectly normal, the coupler terms becomes collinear with the predictor. So it means that it cannot be separated. So how do we test for normality? First of all, we have to use our latent variable score. So use normality test on the latent variable score that the software generates. Okay. The PLS-SEM software, the Smart PLS can generate the latent variable scores for you. And then you can export it using other tools like SPSS, Stitcher, and what have you. And then using the Shapiro rate test, or you can also use skewness and kurtosis. That also help us to get the values for the normality test. Now, the rule is that if the normality test is significant, that is, if the p-value is less than 0.05, the variable is non-normal. And for that matter, Gaussian Copula can be applied. And the reverse is true. If it is more than 0.05, it means that the predictor variable is normally distributed. And for that matter, we cannot go ahead with Gaussian Copula approach. The second requirement is that there should be sufficient sample size. So the Gaussian Copula models need larger samples than the standard PLS-SEM. We have learned that with PLS-SEM, if you have more than 30 sample sizes, you can go ahead with it, right? Now, if you detect or if you suspect that there could be potential endogeneity within your variables, okay, in that case, you need a larger sample size to do that. So this is perhaps one of the reasons why most studies do not report on endogeneity, because if these assumptions or requirements are not met, you cannot go ahead with the Gaussian Copula approach using the Smart PLS software. Okay, so Becker et al. 2022 recommend that you should have more than 500 sample size for a better or reliable result. So if you have smaller sample size, for example, if it is less than 500, then we might be at risk. Our results may lack statistical power. And then one of the requirements is that avoid adding more than 2 to 3 Copula terms, unless maybe you have more than 10,000 sample size. All right, which is not really common, unless maybe secondary data. The third requirement is that there should be a theoretically grounded justification. So we only test constructs where endogeneity is theoretically plausible. And then we don't blindly add Copula terms to every path. Okay, so these are some of the requirements that has to be met before you go ahead with the Copula terms. So if you can justify theoretically why endogeneity is not a concern, and that's if they ask you to do that, in that case, you can go ahead and justify why there is, or why endogeneity is not a problem. So now, how do we interpret the Gaussian Copula results? So if the Copula term is not significant, then we can see that there is no endogeneity concern, or it has not been detected. In that case, your original PLS-SEM result becomes classified. All right. So how do you report that the Gaussian Copula approach was applied to test for endogeneity, and then the Copula term was not significant? That is our coefficient, giving us any value that you get. We are going to establish that with the software, and then the p-value as this, suggesting that the endogeneity is not a major concern. Okay. Now, if the Copula term is significant, that is, if the p-value is less than 0.05, then it means that endogeneity is present for that predictor. In that case, the software also corrects that and gives us the corrected path coefficient, which includes the Copula term. And in that case, that coefficient is more accurate estimates. So we can compare that the original beta estimates with the corrected beta estimates, then report the difference. All right. So the very first thing, as we have described, is that we are supposed to test for the non-normality of the predictor variable. Then we run the Gaussian Copula term in the Smart PLS software. So let's go ahead with the software. So this is the model that we have been working on over the past few days when we started. At this point, is there any questions so far? Okay, so let's move ahead. So as you have already mentioned, once you start, you're supposed to run your PLS algorithm to see. So let me run that. So once you do that, the next thing is to um, test if your predictor variables are normally are not normal before you go ahead with the Copula test. Okay, but you can see the Copula, the Gaussian Copula here, and it's very simple to go about, just like the quadratic effect. Just click on that, and then you select. Just click. So this is the Gaussian Copula term that has been added, right? And then you just run Bootstrap. So we do this when we are convinced or when we have tested for normality, all right? So this is the Copula term, and then I don't know if you can see clearly the beta estimate. So the beta estimate is negative 0.090, and then the p-value is 0.70, 0.789. So the Gaussian Copula term that has been added shows that the p-value is not significant. So it means that the predictor variable data access is not correlated with the error term in Y, which is the behavioral engagement. So it means that endogeneity is not an issue. But first of all, let's see how we can go ahead and test for normality. Okay, we cannot use this software to assess normality. So for the purpose of this class, we are going to use Stata. Okay. I think Stata is part of the classes, the NUGS classes that we are doing, right? So I don't know if some of us
Please,
have.
before you go, Prof,
Okay.
before you
Okay.
go back, before you go to that place, can you help me go back to how you generate the Gaussian
Okay, so the
Gaussian copula? Yes.
generation is just like the one we did yesterday. Yesterday, when we were dealing with the core platform, it is found here. I don't know if you can see. This is the quadratic effect here. So you have select, latent, connect, quadratic effect. So if you want to assess the linearity, okay, you just click on the quadratic effect, and then you click. For the Gaussian effect, the same thing. You just select copula, and then you see that it will change to click. So let me come here. And then let me select Gaussian Copula. You can see this click on. Just select that, click on that, and then the Gaussian Copula term will be created. I don't know if you can see that.
But you said after running the PSLM, you have to go back and run the bootstrap before you can go to the Gaussian. I think that is something that I didn't
Okay,
know.
so what I said was that anytime you open, so let me go back. Let me not save this. So this is our model. Once you open your software, this is how it looks like. All right. So you just have to run your PLS-SEM algorithm, and then assess your measurement and everything. Once you are done, you just come to Gaussian Copula, and then you select. And once you select, you have added the Gaussian Copula term, all right? And how do you see the results? You can only see your p-values in Bootstrap. So you come to calculate, and then come to Bootstrap. You start calculating. Good. And you can see your report in here, open full reports. And then you come to path coefficient. So if you can see clearly, this is the 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 original estimate is digital access and behavioral engagement, which is 0.493. Now we have added the Copula term, the Gaussian Copula term, and that is predicting. And then the estimate, that is a B underscore C. The estimate of the Gaussian Copula term is negative 0.090. But you're supposed to assess to see is this significant or not. So if our Gaussian Copula term is significant, it means that there is potential endogeneity issue. But we can see from here, we have 0.789. So it means that the Gaussian Copula term that has been introduced is not significant. So our original estimate, the first estimate before we added the Gaussian Copula term, the original estimate is conclusive enough. We can report on that. It is reliable. But once we added the Gaussian Copula term, we realized that it is not significant. So assuming that the Gaussian Copula term was significant, it means that this is the true estimate. So let me copy this to Excel. So our focus is on this one. So this is after adding the Copula term. But let's go back and then remove the Copula term and see what happens. So we can select and delete this one. And then we run our bootstrap. So open for report. And then let me copy this one to Excel. So our focus right now is on digital access. And then so before we added the Copula term, our original the estimate was what? 0.401. The estimate was 0.401, and then the p-value was 0.00, right? And then if we suspect that endogeneity can be a problem, if the values in X is also explained or correlated by the values in the dependent variable, the error term of the dependent variable, that is where we have to include this Gaussian Copula term, assuming that all the conditions are met, non-normality conditions are met, right? So now comparing this one to this one, realize that if this was 0.00, it means that the true estimate for this path will be 0.493. And then the true t-statistics will be 1.411. And then the p-value will be insignificant. So now let's check the difference between the original sample and then when we include the Gaussian statistics. So it means that we have negative here. So it means that our digital effect, the one if we didn't consider the united factor, our original effect was underestimated. The beta coefficient was underestimated because this is 0.409 and this is 0.493. So this is the true estimate. I don't know if there's any question with that. Any question?
Yes, I got this, but when I was running, I ran it on a different model. I realized that the Gaussian was significant. for
Okay,
one of
but
them. But
but before
yeah,
before we run this, we are supposed to check for the normal non-normality. Have we done that? So if the data is normally distributed, the Gaussian coefficient can also give us bias estimates. So what I was about to do was to let's assess the normality because we learned that if um, the potential endogenous predictor must be non-normal. So if it is normally distributed, then it becomes a problem. If the predictor is perfectly normal, the coupler term becomes collinear with the predictor. All right. So first, let's assess to see um, if our data set, the predictor variables are not normally distributed. So how do you go about that? First, you run your PLS algorithm without the Gaussian Copula terms. And then you go to open full reports. So one way you can go about it, you can create a data, okay? And then you can create the latent variable scores here. And then you can create that. Or you can come here. Once you run it, you can see that latent in the final results section, you will see latent here. And latent here report both the scores, the correlation, the covariance, and then the descriptive statistics. Okay. And you can even see the skewness in here. So this is the skewness. All right. So now let's see how we can calculate for the Gaussian, the Shapiro-Wilk non-normality test. So another way that I was showing you was that you can copy this one to Excel because you can create a data, as I told you earlier. Let me create that. Once you do that, you come back to, you save this one and then come back. You can see that the data that you just created, the one that you just created, has been added here. So you see NUGS tutorial data set derived from PLS-SEM. So this is the created data. All right. This is the created data. And I can open that and let me see the raw data. Okay, let me see. If the data is created, the values are supposed to not be this. Okay, very good. So this is it. Well, what I was seeing here, these are the raw data. Okay, these are the raw data. So let me come to the raw data again. These are the raw data. So the created data. And this is happening because I also selected the manifest variable. So let me go back and show you that. Let me delete this one. So run the PLS algorithm, go to open full report, and then create data. And when you are creating data, you realize that they'll ask you to select. So I was seeing that manifest variable, the original um, scores, because this was already ticked, all right? So, and then I also ticked the latent variable score. You can also tick for outer model if you want the outer model score, or the inner model score, or any others, all right? So I can take this one. In that case, it will create, you can also change the file name, but automatically it will give you this. So let's call this one latent. Let's rename it latent. And then let's create that. So let me come back. So this is it. It has created the latent variable scores. Now, let me come to the raw data. So this is the indicators, and this is the raw data. Now, these are the latent variable scores. All right. Now, let's see what happens. You can export it to Excel. So let's export that, and let's call it latent scores only. And let's open that. Look at how it has appeared here in the one that we just created. Okay, you can see that it has clustered. So this is what happens when you export the one that the software has created for you. You can work with this. That is, if you know, you can use Python and then maybe how to clean this one. But this is a lot of work. If you have to go by it because it has clustered them by separating them with this comma, semicolon. Okay, and this is going to be very difficult to work with. So the best approach is to not create the data, but copy from what the software has created for you already. So now once you run the data, come to open full reports and then look through the left pane. You will see the latent variables in here. Select the scores. Then copy from here. All right. When you copy from here, this one is the best way to go about it. You can even copy to R. Let's copy to Excel. So now let me see, or let me open the first one that we did. So this is it. So this is 0.701. The same thing is found here, 0.700. So here it has run it to 3 decimal places. And this is very clean. Okay, so I would always advise that whenever you want to import latent variable scores, just copy from the results. Okay, and then go ahead. Don't create and then export to Excel because that one is going to give you class T outcomes. Okay, that is good. So now we have exported our latent variable scores. Now you want to test for normality. And don't forget, normality is tested on our our independent variables only. So what do you do? Let me open Stata. I don't know if some of us have joined the Stata class. Is there anyone who has joined the Stata class?
Yes, yes, yes.
That means this is not new to you. I already have a do file here. Let me open a do file. And you can even use, you can let AI assist you. You know, we are in the dispensation of AI. So even if you don't know anything, at least AI can assist you. So I can ignore this one. Then let's start proper with AI. Okay, so any AI tool that you know. I don't know, are you interested in the AI part?
Oh, yes. We are seeking knowledge here.
Yeah, we are in the dispensation of AI. So you don't have to find yourself wanting. Once you can get answers, or once AI can assist you do certain things that you have never learned before. Mm. Some of these things, most of the things that I've learned, I learned them through AI. So let's try and see how we can go about this with AI. So even if you are new with Stata, okay, so this can be an advantage. Those of us who are also interested in Stata, but it's also good to learn what you already been taught because knowledge, you cannot limit yourself with knowledge, but with AI, you can just be very quick with whatever you are doing. Okay, so now what do you want to do? I have my my listing here, my latent variable here in this file, latent score. So you can go by the manual means by opening Stata and then going to file and then import a spreadsheet, and then you browse and then you come to okay, the file is not found here, so it means that the file format is different. Let me see here. Okay, so I can see the latent file here. Okay, unable to load. So it means I selected something different. Let me go back. File, import. So Excel. Let me check the file format.
CSV or SL? Yes,
Let me
CSV.
check from here. Okay, so it is CSV, right? Good. It is CSV. That's why it was not import. So file, import. So CSV file, you can use the test data delimited. Test data delimited. Test data delimited. So you can come here and then you come to, so now you can see the latent score here. You can open it from here. Now let's see. So it has imported correctly, right? Let me see. I think it was already in sheet 1 and sheet 2. So which sheet is this right now? Okay, so treat sequential delimiters and then okay, let's go ahead and submit. Do you want to continue on this data in memory? Yes. Okay. So it has imported already. So we have it here. So what I can do, I can just describe. So I have my data here. Or just type in BR to open the browser. So this is it. That's imported correctly. All right. So it means that even with the CSV, the one that was clustered, it can even import correctly for you here. Right. So even this one, I just got to know that it is even possible with Stata once you have the file clustered in CSV, and then it will import correctly. But let me show you the AI way so that you can also learn from that. So let me close this one and close this one. So what you do is that you just right click on your file, copy as path. Then you come to your AI. So I'm using Claude. So what I would say is write a short data script to import this file. They just tap enter. So you can just copy that and then open your data. You can select your do file and then paste that in here. So let's see if this will work. Okay, so we have imported that. Let me divide it into two. So this is our import. All right. So what we can do is that we can go ahead and describe. So let's run this. So you have to also describe what is in the software. Sorry, what has been imported. Then copy that and give it to you here. So this is the result of the input. So you can go ahead to rename it. So now let's rename. Let's use the original name seen here, or let's do the variable labeling. So for data access, we can use D because we are using quotes. Okay, it is better to rename them shortly so that you don't have to always be typing this in full. So let's rename the variables with their initials. For example, AO for academic outcomes. You can simply do that as well with data. You just write rename, but because you are letting AI helper, that's why we are doing this. So let's just press enter. So that is it. So it has renamed the first variable, which is ID. And then we can also rename this to AO. So let me run them together. This is it. So now we have this. Let me see what is in this ID. The BR. ID is just the numbering. So it's from 0 to the last. Okay, so that is fine. And then now you can just copy this and give it to AI so that it will follow from where you have gotten to. All right. So now I want to run normality test using Shapiro. And also assess the skewness and the tools. So rather. But you are supposed to prompt AI. The reason why you're supposed to know what you are doing, because the code that it might give you. So let's see what happens. Okay, so it's saying that, but let's take note that whatever we are supposed to calculate or determine the normality is supposed to be the predictor. So we are supposed to make it clearly known. Take note. The predictors are, so here our predictors are B, because B predict AO, right? So let me include that so that we don't do for so B, LS, and PQ. AO is the main dependent variable. So it says that the summarize detail command will help you give it will help give you skewness and accuracy. So let's run that and see. So this is the code. So Shapiro. So it has given us this one as well, but we can also omit the OA. Okay. So this is it. We have the observation the W, V, and Z, and then the probability. And everything is significant here. So it means that this shows that, so what is the Shapiro wave test for normality? P-value is greater than the Z. So this is significant. So we can say that our data is normal, right? So let's give that to AI and see. But let's also summarize this. Let me take and read it. AO from it. So you can also see our skewness in here. Skewness, kurtosis. Skewness, kurtosis. So we can copy all of this and give it to AI as well. We can also help further interpret it. So our predictors return significant p-values, which technically means that it indicates a departure from normality. So it means that it is not normal. However, with a large sample like yours, which is 450, the Shapiro wave test becomes very sensitive and will often flag even trivial deviations as significant. This is well-known limitations of the test at large samples, so the results should not be interpreted in isolation. So now we are supposed to also consider skewness as well. Okay, and we can see that the result from the skewness tells us much more reassuring story. So the Shapiro error is not something that we can rely on. So let's see our skewness value. So BE has negative 0.00000, negative 0.022, which is very close to zero, right? And this is close to zero as well. Close to zero. This is close to zero. So all the values are close to zero, plus or minus one, which is within acceptable range. And then the kurtosis values are also very close to 3, which is the best benchmark for normal distribution. These values collectively suggest that the distribution are approximately normal. So because this is between +1 and -1, it is considered to be normal. And then this is also close to 3. So in conclusion, we can be convinced that our data set is normally what? Distributed. Is that right? Do you all agree?
Yeah.
Okay, that's fine. But let me see the code again. Mhm. Okay, so that is it. So based on what we have found, our data is normally distributed. So we don't even have to go ahead to, we can justify, if we are being asked about endogeneity issues, we can justify that our data is what? Normally distributed. One, it does not meet the assumption for non-normal data. Okay. So probably most of the studies that you see around, they run this and then they they have the results that the data is not normally distributed. That's why they don't go ahead with the Gaussian Copula approach. I don't know if there's any questions so far. But if the data is normal, that's why you can come ahead with the Gaussian and then you click, then you report it like we did here, compare the result and then report the difference. Was it overfitting or underfitting? That is all. Any questions so far?
Yes, I want, please, if you can go back to how you show the normality test from the smart PLS.
How I show the normalities test in Smart PLS.
Yes.
As you open the software, this is
Yeah,
it.
you know when when you did the software, yes, please. How you test for it.
Oh no, the software does not give us this capability, but you can find out for the skewness. But for the Shapiro, you cannot test that.
Okay.
So let's see.
The skewness.
So let's go to open for reports. Let's check something here. So if you want to find out for the skewness, you come to the data set. So you come back from the workspace area and then select the one that you want to run. And when you select that, double click, you realize that you have the descriptions, the descriptive statistics in here. So you have the mean, standard deviation, and then when you scroll to the right, you can see the kurtosis and then the skewness here. So this is the skewness and this is the kurtosis, right? So this is what you can find from the software. So this is the original sample as well. You can also see this. So these are the skewness for each of the indicators, right? I don't know if your question is answered. So
Yes, please. Yes,
if you're familiar with SPSS, you can also go ahead with that, and you're going to get the same results. But I think that data is also very simple to go about, and then so if you want to be a researcher, you cannot learn only one software and then in isolation. You just have to also have some knowledge about other software as well, so that what one software cannot work on for you, you can go ahead with um and do it that way. So in Stata, you can see
So
that we
please.
have
Mm.
structural equation model here. SEM, structural equation. Okay, go ahead and talk, please.
Yes, please. When I check, there is some Kramer Vomis p-value. What does that want to mean? Is it the same as the normal p-value?
Yeah, the camera is I think it's an assessment for it also helps us to be informed about the normality. Okay, and just like the Shapiro, we have the cameras as well, and that is
Okay.
somebody's assessment. So Shapiro is somebody's name, and he has his own assessment, and then the camera is also another way to assess that skewness is the same way.
Okay. Okay. Thank
Mhm. So this is the interface for SEM in Smart PLS. I think I go ahead and build some models in something like that. So that is the class for endogeneity. Let me see if there are something to be done in the slides. So this is the interpretation, the report. You just have to compare your original estimate with the Copula term, right? And then the GC coefficient. So let's see that here. This is the original sample mean, 0.400. And this is the GC estimate, which is negative 0.9. And then so I can create new insert here and call here the Copula term. So Copula estimate. So this is the Copula estimate, right? Because this estimate is as a result of the GC term here. And I'll also create another one. So the original sample mean will be here. And then our GC, our GC coefficient will be here. So I can clean this one. And then I can also delete this one. Because this is the sample estimate. So I can report on these ones. That is all. So that is the case that if your GC coefficient, the Copula term, gives you a significant p value. But our case, it was not the case. But assuming it was significant, this is how you're going to report it. The original estimate, the Copula estimate, and then the GC coefficient, that's the Copula term. And then the standard deviation of the Gaussian coefficient, and then the t-statistics and its p-value. Then you talk about that. So this is, I'll send the sample size in the group. Now let's look at some of the best practices. Always check non-normality of prediction first, and then use control variables as the first line of defense. So let's see how we can include control variables in our data set. So assuming that we want to control for age and gender, all that we do is that we just make sure that you have select here and then gender. So you can bring it here, gender, and then maybe if you want to also control for age can also come in here. So the control variables are always mapped to the dependent variable. So let's see. So what you see here are control variables. So let's run the PLS-SEM and let's check the bootstrap. Are they significant or not? So path, and then become 2. So you can see that age is not significant and gender is also not significant. So these are not omitted variables, right? So you can decide to include these as control variables to demonstrate that we've not omitted potential variables that could have affected the dependent variable. But here it is giving us 0.7, it is about 0.05. All right. So this is the control variables. Let's control for level of studies as well. So select and then you move it here and then okay, connect. And then run the PLS-SEM bootstrap and then run the PLS already and then run the bootstrap. So let's see the results. You can even see from here, they are not significant. And see from here, 0.75, 0.2, and 0.15. Now also go to the full report, path coefficient, and then this is it. All right. So these are the control variables that we are talking about. Apply the Gaussian Copula as a robustness check. So as part of your robustness check, you can use the non-linearity, and then you can also use the Gaussian Copula to demonstrate that you are not being affected by linearity. Report both original and then the corrected path coefficients. Limit Copula terms to variables with theoretical endogeneity risk. So you don't just go ahead and then be applying the Gaussian Copula to the path. Only if you have theoretical reasoning why you think that this could be could be at risk for endogeneity. And then you use Bootstrap with at least 5,000 subsamples. And then there are proper sources that you can cite, the Holt, Ital, Becker, Park, and Gupta, and the rest. What are some of the things that you don't have to do? You don't have to apply the Gaussian Copula if your predictors are normally distributed. Don't add Copula terms to all paths blindly. You have to be selective and theory driven. Okay. So don't use with very small samples. If your sample size is maybe less than 200 to 300, it might not give you a reliable estimate. And don't add more than 2 to 3 Copula terms unless you have a very large data set that is above 10,000 plus. Don't treat a non-significant Copula term as a proof of no endogeneity. It only means that it is not detectable, right? Endogeneity is not detectable. So that's how, when we are reporting, we have academic writing terms, okay? So we don't see that there's no endogeneity, but you can see that endogeneity is not a concern, all right? It's not much of maybe a concern, endogeneity is not detected. So that's how we put it. Don't forget that this is an instrumental variable free approach, so it is a useful tool, but not a perfect substitute for strong research design. So we may mention that if you apply solid or valid instrument variable as a means to check for endogeneity, that is a valid way to go about it. But it is not easy. It is not very simple to get a valid instrument. So if you get an instrument and even it is weak, it is going to give us bias estimate. Okay. So endogeneity is a very serious concern. It is still something debatable, and probably one of us can come out with, models that will help us to better estimate endogeneity. So I think that will be for it. I've also added some reference materials for your studies. Some of these things, if you really want to get the understanding, you just have to always be reading more materials, and then I think you'll be good. So I don't know if there are some questions that I have to answer. Other than that, then we can draw the questions down for today's class.
Okay, yeah. Basically, I just want to add, when we were treating the endogeneity, you said we shouldn't state that endogeneity is not found or endogeneity is absent. You should rather say it's
I
not
mean, you don't
significant.
write no,
Even
no,
if
mhm.
endogeneity.
There's no endogeneity. Yes, yes.
Although
I
if you
mean,
have done
you
the
can just
test
write
and
that
you realize that
endogeneity
it's
is
not
not much of
significant.
a concern. I don't know if you got me, or you can come up with your question again.
Yeah, I'm saying, what if you run the model and you realize that the endogeneity, the value is not significant? So you said that it's still not detected. That's what I'm going to say.
Yes. So are you saying that if it is detected?
No, if it's not detected, if it's not significant. Yeah.
Oh, yes. So let me see. I think I reported something here. So the Gaussian Copula approach was applied to test for endogeneity. The Copula term was not significant, or you can say statistically not significant. Then you report the estimate. So this is the Copula coefficient, and then this is the t statistics, the p-values, which suggests that endogeneity is not a major concern. So I didn't state, or it was not stated that it is not, or there's no endogeneity. No. So we have learned that we have four different types of endogeneity. We have the omitted variables. So the fact that you test that does not mean that every variable has been considered, because already your R square is not even that high. It's not, there are still some aspect of the different variable that has not been explained. All right. So we just mentioned that it is not much of a concern. All right.
Yeah, basically my question has to do with when you use instrumental variable and
Instrumental
you test
variable is
for
not
it.
applicable with
Uh-huh.
um you cannot apply instrumental variable. So with SEM, with PLS-SEM, the smart PLS software. So if you can check from
Yes.
here, uh-huh.
Yeah, my concern was that it's not have to do with using the PSMA PSL model. I was saying that in writing, saying academic writing,
Mhm.
you don't say that the endogeneity is not
I mean,
detected.
don't mention that no indigeneity. You can just say that indigeneity is
Yes.
not detected, yes.
Okay.
Or you can say it's not much of a concern. There are certain terms that we use in research. Uh, so you just have to, harbour that a bit, and then that one you are safer that way. Hmm. There are certain claims that you cannot make. That's why sometimes, even if you are writing your gaps, okay, You don't see that no study have found, because have you been able to go through all the studies in the world? Every single day, journals are publishing, and even publication started so many years ago. Even 1940s, we have papers that were published in 1940s. So just to say that no study has done this is very, so sometimes you just say that maybe to the best of, sorry, to the best of the knowledge, or to the best of our knowledge, there have been limited research. So that one is better that way than to say no research. Okay. But you can say that to the best of our knowledge, there have been limited studies or there are limited understanding of this and that. So these are some of the technical research terms that have to be applied. Okay, than to say or to just claim with certainty. Unless maybe you can justify why you're saying that, that is fine. But I think that some of these habits are good to harbor. Exactly.
Yes.
Okay, thank you. Any other question?
So my question has to do with mostly when you run the analysis and you look at the various uh, results, like maybe you are looking at the p-values, you are looking at the uh, what's the name? So those values, and you see that some of them does not meet the threshold we're looking for, where they will be indicating red. How do we normally go about that one? Because I don't know whether we can just report with those ones direct, or like we need to do something about it before we can report.
Like if you get insignificant results, is that what you mean?
Yes, Doc.
Ah, but it can be a problem. The whole research that we have been talking about, it's sometimes about you and then uh, the corresponding reviewers that your papers will be with them, right? And it's much of concern that you do a study and everything is not significant. So if it's not significant, then the question will be that why did you go ahead to do it? Are you just here to prove that it's not significant or what? Uh-huh. So I think ideally it will be of much help that at least you should have some significant results so that you can better discuss and then give better recommendations. Because if you don't have significant values, then how do you recommend? What is the implications of your study? So getting 100% insignificant results, you might have to go back and check your model, check your studies carefully, why some of these things are occurring. But it is even possible to get everything significant. And it is not always the case that if you get insignificant for some of your results, it is not good. No, there might be a reason why it is the case. That is why we have that discussion part of the study. We are supposed to discuss what this means. Why is it the case? Why is it not applicable? So sometimes if it is not significant, it means that the thing is not applicable within the context within which you are looking out for. Mhm. So all of these things are justifications that has to be discussed within the discussion session of your study. I don't know if that is clear, but 100% insignificant, then you cannot recommend. What are you going to tell people or policymakers? Is that clear?
Yes, Doc.
Mhm. I don't know if you have encountered that, but I've not really seen that so far.
Not really, but
Mhm.
sometimes you
Yes,
get some, yeah, like maybe
but
two, or yeah.
yes, but we don't do research with the hope that we get significant. I mean, don't focus, don't be expecting significant results. I mean, such that when you get insignificant, you'll be so worried that why is it that then you want to, I mean, try to make it no, no. So some can be significant, some might not be significant. But I know that if it is significant, that's why you can give policy recommendations and the rest. But if it is not, then it is going to be very big problem. So that is it.
No
Okay,
P
thank you.
hacking. No P
Okay,
hacking.
please go ahead.
No P hacking.
You said no.
P hacking. No P hacking.
Yes. No P. Yes, no P hacking. Your expectation should not be getting P hack like getting P values that are 0.00. No, not at all. So that is you're supposed to be transparent. I think the last time I showed you a paper how we reported on that. Yesterday, yes, yesterday you saw that.
Yes, Doc.
Um,
Yeah.
what was it about? It was about the RSME and then the ME, where we realized that some of the LM, the linear model root standard mean error was giving us much lesser error compared to the PLS-SEM. So we reported on that. So we have to be transparent, and that is our job as researchers, so that we can give better um, estimate and reliable conclusions. And that is why we have limitations in study. Every study has limitations. So we report on, okay, so this is what we found, and this is what we think could be the problem. And so these are limitations. So further studies might go further to do this and that. That is it. So you have to be transparent, and then we treat, if there is anything that has to be treated with caution, you have to let the readers know so that decision makers can be rest assured and your conclusion can be reliable. So we just have to know that not every research has its own inherent limitations, and it is normal. It is completely normal. So I think our time is up, but I'll just stop recording for now.